we have SIMsalabim, which is it's pretty good. There's some really good names of some of these talks coming up from Marius and Tomasz. Come on up. We're going to learn about some really fun hacks with SIM cards, the computer inside of your pocket. So.
Does it work? Yeah, I think it works.
All right, here we are live. All right, hello everyone. I'm Marius.
I'm Tomasz.
And we are here today to show you a couple of tricks and magic with SIM cards. A little bit of background about us. I'm working as assistant professor at the University of Birmingham. That's in the UK, not in Alabama. I used to play a lot of CTF in the past. Now I'm busy researching. And what I'm researching is everything around low-level security, like fuzzing, binary analysis, rehosting, and relevant for this talk, cellular security.
And I'm Marius' PhD, and I usually try to incorporate my work into my demo scene things. And in general, I'm really interested in low-level software and hardware, with particular interest in cellular security.
Yeah, so that's enough about us now. Let's start right with a small trick. So we have a phone here.
Yeah, we have a Pixel 6 with the SIM removed. And let's just,
okay. So you should see here, like ignore the terminal for now. You see the screen of the Pixel 6.
Yeah, so I'm going to insert it. And there we go.
Do you want to see a magic trick? Yeah. Yes? Okay. And here we go. We are on the website of reverse.io.
Yeah.
Welcome to the conference. We're happy to be here, and that was our first trick. We launched a browser from a phone. But how did we get here? Let's take this motherboard of the very same phone as a little roadmap, as a guidance through our talk. It's conveniently located in a circuit board location area. Just want to know that's fun. But we start talking about the SIM interface.
Yeah, so with the SIM interface, we're going to look at the logical protocol and the physical layer a little bit.
Then we will talk about basebands and how basebands interact with the SIM interface.
Then we're going to take a look at the attack surface and how we can attack the things that we're going to talk about in the SIM interface part.
And the good news is our attack surface exploration also leads to vulnerabilities, which we will very briefly describe later on.
And lastly, we're also going to take a look at these interposer devices, which are going to allow us to do some interesting attacks that don't require any modification on the SIM side of things. Okay, let's start with the SIM interface. So you've probably seen your SIM card before, and there are a few pins, not many. And the one that we're really interested in here is the I/O pin. That's going to be our attack surface for today. And this pin implements the protocol, the logical protocol used to exchange messages back and forth from the phone to the SIM. And the way that this works is this. The phone will send a command that looks roughly like this. There's a class, instruction, parameters, and some data, the data being optional. And once this is sent to the SIM produces a result, a response in the form of data, which is also optional, and a status word made up of 2 bits, SW1 and SW2. And this kind of goes back and forth, repeats over and over again, kind of forever, essentially. But what's important to note here is that this flow always goes from the phone to the SIM and never the other way. So if we take a look at the physical layer, we kind of start to understand what the protocol looks like, and it really looks like UART with a clock, which is USART. So on the top there you can see this is the UART essentially exchanging data, and you can see on the right side, if you look at the right side, you have 5 bytes. And these 5 bytes are the header of that APDU. And you can see the CLA, the instruction, P1, P2, P3, and they're encoded in a way where the I/O line will go low for one cycle, it will go up, and then you will have the 8 bits of information, and then it's followed by a checksum bit. And it's, of course, synchronized by this clock, which is, in this case, 3.5 megahertz, and each character takes a certain amount of clock cycles to happen. So we can actually invert the flow. So I said before that it always goes from phone to SIM, but there is actually a way to go the other way, but it requires the phone's cooperation. And we do this through something called proactive commands. So with proactive commands, the phone will send, as usual, its commands to the SIM. And this can be anything, but the status APDU is the one that is usually used to poll if there's nothing else happening. But if there's like file reads or etc., it will repurpose those other commands. And basically what the SIM will do is it will perform the requested operation, and it will respond of the response APDU, which is the data and status words. The difference being that when there is a successful execution, meaning that there is going to be a 9000 status word, so 90 for SW1 and 00 for SW2, this indicates a successful execution of a APDU command. But in this case, the SIM can actually take over that status word, and if it's 9000, it can overwrite it to 91XY. And 91XY indicates that there is a proactive command generated by the SIM, and it allows the phone to then request this proactive command with a fetch. So it can fetch, so it can send this APDU 80120000, and then it provides the XY from the previous response. XY indicating the length of the command, of the proactive command. And then the SIM will respond with the proactive command encoded in this ASN1 BERTLV, which stands for Basic Encoding Rules, Tag Length Value, and I'll discuss that in the next slide, and the regular 9000 success status word. So let's take a look at an example of a proactive command. So this is just a blob, and I highlighted some of the bytes. So it begins with D0. This is the tag, and this indicates that it's a proactive command. Then is followed by some yellow bytes. This indicates the length of the proactive command, and then again, blue indicating a tag, which describes some particular element, followed by length and followed by value. And these can actually nest within each other. So I'll show this in the next slide. So here, each of these lines indicates a block, individual. They call it a TLV because there's a tag, length, and a value. So there are multiple tag, length, and value objects, and each indicates a particular element of this proactive command. So if we decode all those bytes, we get this, which means that there's a proactive command, and inside of this proactive command, there are multiple elements, and they build up a setup menu proactive command. Setup menu has a particular configuration using the qualifier in that first command details object. Then it's followed by device ID, which indicates the source and destination, because actually these proactive commands can also flow from the SIM directly to the network and also to other destinations. Then there's the alpha ID, which is, for this particular command, is described as the title of the menu. And then you have multiple items indicating the items of that menu, including the strings and the IDs of those. So the trick that you just saw, the first demo that we had, it also used proactive commands to perform that browser opening. And this is that exact payload. So if we decode it, you can see it again. D0 indicating this is a proactive command, 3C indicating that the entire remainder of those bytes is part of that command. And then if we decode it, we have this, which is command launch browser. As you saw, it launched the browser. Launch browser if not already launched. So this is a qualifier, this parameter to this command, indicating how it should be performed. It came from the UICC to the terminal being the phone. The browser ID should be repurposed, so the default browser should be used. And the URL we set to is just a regular string and encoded as ASCII. And the alpha ID for this particular command was used as the confirmation message. So the SIM can actually do even more than just the proactive commands, and there are many, many different proactive commands. It can also do this interesting thing called remote management, and this actually allows a operator or issuer of the card to install apps on the SIM. And installing these apps on the SIM doesn't actually require any user confirmation. And the capabilities of these apps include also opening browser and many of the other things we will show. But the capabilities of the apps that are installed on the SIM are very much dependent on the capabilities offered by the phone. And these capabilities offered by the phone are actually told to the SIM with this special APDU called terminal profile. And the terminal profile it essentially consists of at most 30 bytes or right around. And every byte is essentially a bit field indicating whether a feature is supported or not. And there's obviously many different features. And you can have some fun with this, right? If you update the menu as fast as you can draw graphics using that SIM menu.
So this is all, or these are all capabilities SIMs have, which are according to specification. Now we were interested what if happened if a SIM was not following the specification and tries to do malicious, hostile operations with the baseband. And to understand what could go wrong or what could happen, we need to look a little bit into the basebands. In this case, we look in the Samsung Shannon baseband as present on the Pixel 6. So the cellular basebands, they are their own dedicated processors called CP or cellular processor, which runs next to your so-called AP, the application processor, which has Android or iOS based on your phone model. The firmware on the baseband processor is highly, highly proprietary with a lot of lines of code. It has so many different lines of code because it needs to implement the full cellular standard. All the different specifications over multiple cellular generations are embedded on there running in the firmware. Usually, this is organized in a real-time operating systems, and the different parts of the specifications are embodied in different tasks in the real-time operating system. We will get to this in a minute. Of course, the cellular processor needs to talk to the outside world, and it has multiple interaction points, right? First of all, it has shared memory to talk with its application processor, because sometimes, like, if you get a call, you get notified on the AP there's a call. So there's a communication between CP and AP. Then, of course, the CP needs also to communicate with the cellular network over base stations, so it has RF peripherals, and other accesses to the over-the-air interface. And interesting for our talk, it also has a peripheral to speak with the SIM. So we can look into what comes in and what comes out over the SIM interface. So we took the baseband firmware and started reverse engineering how this particular baseband would interact with the SIM from a firmware perspective. And this requires, to our findings, cooperation of a lot of different tasks. Here we have two examples, for instance, the AT task. You can send AT commands from your application processor to the baseband, and parts of these ATs also allow you to trigger information from the SIM card. So that's why the AT task. There's also the the vulnerability management tasks, which is just there for general network operation. And of course, this also, in some cases, needs to query data from the SIM. So if these different tasks want to speak with the SIM, they send a message via the real-time operating system to the according task, the SIM task. The SIM task then communicates with the UICC peripheral. So this is a physical small peripheral on the die, which is connected to basically the SIM slot where you push in your SIM card. Then also what the SIM task does, it communicates with the user task, so the universal SIM application toolkit tasks, which implements all the parsing of the proactive commands Tomasz just told us about. While reverse engineering the baseband, we also found a couple of other tasks which have SIM in their name. We did not dive too much into their detail. We suggest, or we think that SAP here stands for the SIM access profile, but we did not really look too much in depth into these tasks. We focused on the left-hand side of this image. Also, a small note here. Cellular security or in general cellular specifications use a lot of acronyms. Sometimes they're even equivalent. Like we talk about proactive command, we talk about the user, the universal SIM application toolkit. It all means the same, and there are other abbreviations referring to the same, like the SAT, the SIM application toolkit, or STK, again, SIM toolkit. So all of these are more or less usable interchangeably. Now, let's see how the SIM task actually implements the low-level interactions with their respective UICC, with the peripherals holding the SIM. The SIM task has a driver layer, PAL driver USIM, which implements this low-level communication. And it communicates with the SIM in 3 different ways. First, there's a GPIO interface, which is connected to a couple of different GPIOs related to the SIM. For instance, the SIM detected or SIM reset, which just checks whether the SIM is inside the phone or not, or whether there was a reset triggered by an external kind of means. Then for actual data communication between the CP and the SIM, it uses memory mapped I/O. So there are some memory mapped I/O ranges where the firmware can directly write to and read from to have interactions with a UICC peripheral, which will then accordingly pull the data from the SIM card. For instance, there's a data register which can be used to fetch the data from the SIM or write data towards the SIM. Last, as channel, there are interrupts or IRQs, and the SIM or the UIC peripheral can use these to notify that some event happens, right? For instance, there could be data available which needs to be read now, or the card could have been removed, all sorts of different interrupts. That's the low-level communication between the SIM and our baseband. Now, for proactive command parsing, there's a user task, right? The Universal SIM Application Toolkit. And this has a lot of different functions, but there's one really large function which is responsible for the decoding of incoming proactive commands. So this is in the baseband firmware. We reverse engineered it, stared long enough at it, and we saw that this function verifies the attributes of the incoming commands. For instance, if it's supported according to the terminal profile, if the length looks all right, so basic verification. And then this task will decide whether the proactive command can be handled locally, so this means on the CP itself, or not locally, in which case it would be forwarded to the AP, the application processor, because maybe it needs to handle it. Of course, there are also some deny lists for certain proactive commands, so it could also be that a command is not handled at all. Now, to understand which proactive commands are actually there in the firmware, we could reverse this task even more, but it turned out very tedious. So we turned to one of the greatest reverse engineering programs of all time, strings. And using strings, we could already find which kind of proactive commands are supported by the phone in question or by the baseband firmware in question. Among others, we see here the launch browser. We also see some about run AT commands, really a lot of different proactive commands, partially with scary stuff if you think from a security perspective. But all of them need some kind of parsing, right? Tomasz told us that there are BAR TLV encoded those proactive commands, so lots of different parsers. And my intuition is usually if there are lots of parsers, there's also a high chance that there are a lot of bugs. And this brings us to the second trick. So,
So here we have the SDK services on the bottom, and that produced by the SIM. We have some debug information on top, and then we have the setting.
So we ask if we want to see another trick, and we do see here that the CP crashed, like the cellular processor crashed, with a payload delivered directly from the SIM card. In this case, we triggered it manually via manual interaction as a proof of concept, but this could also, like the first trick, be completely automated, pushed by the SIM upon insertion. So this brings us to the next part of the talk, the question of how did we actually get here?
Yeah, so let's take a look at the attack surface now. If you're trying to build a malicious SIM card in software, you're really bound to a few things. And first of all, most of all, you're bound to hardware. The most common way of developing SIM cards or in software is with Java cards. So you can create applets, and then you can install these applets in very much the same way as your operator would be able to install them on your phone or on the SIM card. And this has a lot of drawbacks that I will describe in the next slide. Another alternative is using a proprietary programmable card. This is this is a lot less common, even from practice. Maybe there's Multos and other options. It's extremely rare to actually find these cards in the wild. And then the last alternative is a hybrid of the two, so hardware and software, where you have, for example, machine-in-the-middle devices where you plug them in between the SIM and the phone. You can then, of course, rewrite responses from the original SIM. You can also prevent particular commands from even reaching the SIM. And you can maybe inject even your own commands into that data stream. And then lastly, there's also a device called SIMtrace2, which is really one of the only one of its kind, which allows you to actually forward messages from the SIM slot over USB to the host and then connect virtually any PCSC connected card with a regular reader, as you would, to that phone. So this is the SIMtrace I was talking about. And on the right, you can see this SIM-shaped adapter. So you slide this into the SIM tray, and then all those traces there, they just go directly to this board, which supports the 7816 protocol, as I described before, and it forwards this to the host. There's a few limitations, but it's pretty neat to use because then you can also trace the communications. So not only can you select which card you want to kind of use, and you can have 5 or 6 readers attached to your desktop, and you will just be able to choose in software which one you want to kind of go for, and then you can also overwrite and rewrite the communications. So what are the challenges of actually developing Java card applets? And by far, this is also what we used for our demos here. The first and the second demo was a Java card applet that we installed on these cards. And the real problem is, there are really so many problems, but the primary ones are that the iteration time is extremely long. I mean, to install even these small applets, to do these very small tasks, it took an order of like 5 to 15 seconds to flash them, and it takes another like 5 seconds to delete them. They're extremely hard to debug. That's why you've seen some debug information in that second demo, because that is pretty much the only debug we get out of this card, out of the applet, because these are secure elements by design. So it is supposed to be very difficult to extract information out of them. And lastly, when you're developing applets, the card just will reject it sometimes. It will just decide this applet is not right for me. I don't like it, and it will just reject it. And you don't really know why, because it's not going to tell you why. It's not going to give you the reason in the status word, even though it could. It will just reject it. And changing maybe the order of conditions in an if statement is magically fixing it. And another limitation is if we actually compare the performance of these cards, and we compared our fastest card, or we tested our fastest card, and it only reached around 0.2 MIPS. And we compare this to a computer from the 80s, Amiga 500, which only runs also at 0.175, which is marginally only slower than our SIM card. And just to give you an idea, we run these 9 million instructions in around 44.5 seconds. It's extremely slow. If you want to do anything elaborate, it's not fast enough for you to do that. So what we propose is this thing that we've developed called Simurai, and really it consists of a few components, the primary ones being software ICC, which is a ICC framework, so it allows you to build essentially any smart card you would like, be it a banking card or, in this case, a SIM card. And then there is also software SIM, which is the actual SIM emulator. It kind of extends that software ICC, or uses the software ICC framework to build a SIM-like smart card. And really, it's pretty accurate. We've compared it to, we've also run it on like real 2G, 4G, 5G networks, and it really it just works. So it's pretty cool. And from the ground up, we designed this to be hackable and so to allow you to do like research on it really quickly. So it's really convenient to use. You don't have to worry about any keys or bricking your card or using flash writes when you're flashing those applets. You're not worried about any of that. And it really allows you to have full freedom as you would with any kind of software. So if you look under the hood of Simurai, you essentially see this design. If you look on the right, you can see the CAPDU, which is the command coming in from the phone. And then what's coming out is the RAPDU, which is the response that the SIM produces containing that data and the status word. And if we trace that CAPDU, it first goes through this I/O layer. And what we've created there is a virtual card reader. So it will appear as like a physical card reader, but internally it is fully and completely software, and it's always plugged in, quote unquote. And then it goes to this CAPDU, then flows into this demux. And this demux selects how this APDU command will be handled. And you can override these handlers with a lot of them pre-implemented on the software ICC side implementing the very default ones for that any smart card would really want to handle. And the software ICC framework also contains a file system. And this file system, a SIM card contains a file system, but it's not exactly like the file system that you're familiar with, because it actually differentiates between multiple types of files. One of them being just a regular blob, but there's also another one for storing like records, for example, contacts or SMS messages. You also have another type for storing these bare TLV objects, like I discussed for the proactive commands. You can also store them as a special kind of file. And you can also see here that we have special APD handlers just for the software SIM side of things, because there are certain things that we have to handle in a very special SIM way. And then it flows back, and you can do some rewriting on the RR block to rewrite the message that comes back, so the response. So if we could take a look at a typical setup. So this is a very typical setup for us and probably for many others. You have a phone and two phones in the middle. You have the SIM trace underneath plugged into one of the phones. The other one just has a regular research SIM in it. And then it flows through that USB cable to the host, and the host is running SIMURAI. So this way, you can very conveniently, in a Faraday box, as you can see here, with the SDR underneath, on top of that workstation, you can test a lot of different things. So we wanted to use the software infrastructure that we built to do some fuzzing. So the first and obvious thing that we tried was black box fuzzing, and we called this tool MEFuzz. And the MEFuzz was just built on software SIM, and its only purpose was to connect to COTS devices, so common off-the-shelf phones via the SIM trace 2. And it was supposed to send just a bunch of proactive commands and test what crashes and what doesn't crash the target. But it turns out that when you send a lot of proactive commands, the phone doesn't really like it. So it's gonna ignore some of the commands, it's gonna delay some of them, and sometimes it will run like 10 in a row and then just stop and ignore you forever. So we didn't really find any crashes with this method. So that's kind of sad.
Yeah, but our talk is not over yet, right? It's not that we just built all of this software to try some black box fuzzing and then it didn't work. No, we then turned on and went to emulation. We used firmware, which is a full system baseband emulation platform. It's open source, you can download it and use it as well. And it has support for Shannon-based firmware as it's running on the Pixel 6. Maybe not exactly the Pixel 6 firmware, but from older phones model, but the support is there and we thought it's close enough. Also firmware as default, it had a lot of fuzzing from the beginning, so there are fuzzing capabilities built in, but no support for SIM cards. So we thought it's a perfect match. It's very great to connect SIMURAI to firmware, and that's what we wanted to do. If successful, this gives us really good capabilities for fuzzing because we get high execution speeds, right? We run faster than on a physical phone. It becomes scalable because we can spin up multiple emulated baseband instances across multiple computers or cores. And we get introspection capabilities because now we can actually see what happens when we send all those different payloads to the emulated basebands. And we don't get all those annoying resets we had on the physical phones. So what did we need to do to connect SIMURAI to firmware? We needed to implement two Pi peripherals, it's called, so peripheral abstractions in Python, mocking up the GPIO communication channel and the USIM communication channel, like the UICC peripheral interaction. And to get the USIM peripheral, the UICC peripheral implemented, we needed to execute 3 steps. We needed to reverse engineer the USIM interrupt state machine to be able to deliver interrupts at the same point in time and knowing when to provide input and when to fetch data from the data registers. We needed to implement interrupt support so that the UICC peripheral can send interrupts to firmware. And we needed to somehow enable the connection between SIMURAI and firmware. And we used for this the PCSC middleware, which SIMURAI already uses. So we could just hook it up and be connected. Now, the most work-intensive part of all of these 3 steps is probably the reverse engineering and understanding of the USIM interrupt state machine to be able to have the peripheral or the Pi peripheral behaving accordingly. So let's look briefly into this. Luckily, in the driver layer, there is one nice function, which is kind of the main driver for a state machine, which defines all the different states. Like driver is no sim, so we don't have a sim yet. We are waiting for the acknowledge to reset, or we are in the protocol parameter selection phase, or the driver is in a state where it would wait for a command to come in, and then there are different states regarding transmitting and receiving of data, state 5 through 7. And then in state 8, we have a driver as unknown. So we reversed engineered this one big functions, and we got these 9 states and tried to understand the state transitions. In these functions, they are embedded by just writing a value like between 1 to 9 to a global variable. And looking at the function, we got the following transitions, right? Like, it makes sense so far. We can go from no sim to waiting for acknowledge to reset and the protocol parameter selections, getting over to waiting for command. And then we looked further, and we did not find any transition directly to state 5, which is RX TX, or driver as TX RX. And yeah, we looked further. So in the end, there are state transitions missing, which we would need for a proper state machine here, right? So we needed to go deeper and reverse engineer more. And we found that there are a set of other functions which are asynchronously also driving forward the state machine by switching or by writing different variables into the global state variable. And looking at this, we get these additional state transitions. So now it looks already a little bit better, but it's very convoluted. And we don't really want to implement this for our peripheral. So what we did, we tried to simplify what's going on. And for simplifying, we can take 2 easy assumptions. First of all, we only insert a card and never remove a card. And second, we just behave how the firmware want. So we are not going into this driver as unknown error state. So simplified, it looks something like this. And we suddenly have a sane looking state machine where we can go relatively straightforward in state number 3, which is the driver is wait for command. And from there, we can transition to the TX RX state, which then selectively goes either to transmit or receive. So having this all figured out, we implemented the USIM Pi peripheral and could get our fuzzing setup up. And that looked something like this. We used asfuzzer AFL++, and we had Samurai initializing the USIM and the user task. So we start firmwire, connect it to Samurai via PCSC, and just have it running. Effectively, this is now firmwire with SIM support, right? The emulated baseband thinks there's a SIM, and we can communicate with it as usual. After all of this initialization, we took a snapshot. The reason is for fuzzing, we really want to not run the lengthy initialization over and over again. In the initialization phase, there are, I don't know, approximately 100 of messages exchanged between SIM and baseband. So we definitely want to skip this. We took a snapshot. And then we had our fuzzer, our fuzzing harness, directly targeting the emulated user task, which is the task which implements the proactive command parsing, as we remember. And yeah, with this, we started the fuzzing and get to the next part of our talk, which is vulnerabilities and found vulnerabilities. So here's just one image, one instance where we had AFL++ running for, I think, around 2 hours here, and we already have 20 found crashes with a large corpus. We had an initial seed corpus also generated by Samurai tooling, so we had a little bit of valid commands as initial seeds, and yeah, could find a couple of crashes. So let's look at one of the ones we found. Firmware gives us logs from the emulated baseband, and this is a lot of the text. We will get through it one by one in a minute, but firmware really gives us these logs and introspection capabilities, so we can walk through it, right? At the very beginning, at the top here, we have the AFL user task in the square bracket, sending a message to the user sync or to the user task. So our fuzzing input is delivered from AFL++ to user. Then the user task starts processing the input and eventually prints here as a log output that we are proactive commands sent as SS. So we saw this as string before. It's one of the different proactive commands supported by this baseband. It processes it, goes into a decoding function, The user decode SS string, and then it crashes. In this case, it crashes with a PAL memguard corruption. So a heap corruption has happened. Some sanity canary checking on the heap failed, and the baseband just crashed. This is just one example payload. We found also other ones leading to straight stack overflows or direct corruptions of the program counter. So quite some bugs.
Yeah, so the ME fuzz we created didn't all go to waste. Now we could actually repurpose it for a different thing, which is to replay or test payloads. So this is extremely handy if you want to just test virtually any payload that you'd like to test against a real device. You just put it into SIMRI, it goes through SIMtrace, and you're just sending it to the device. And the thing that we were doing before that is making actual applets. And the problem with applets is that the SIM card really wants a valid proactive command. So it will really only allow you to control all the bytes after D0 and the length. Like it really only allows you to change that portion. And even then, sometimes you'll encounter that the applet just gets rejected by the card. But in this situation, you really cannot use the applets to test any exploits that you'd like. So yeah, we repurposed the ME fuzz for that. And the cool thing is that we actually found a few vulnerabilities. 2 of them being SendSS, which is supplementary services, and 1 of them being SendSMS, right?
Yes.
So we tested this on the Pixel 6 and the Pixel 8, and the cool thing is that we actually were able to crash the Pixel 8 only a few weeks after it came out, like 2 weeks, I think, right? So that's pretty cool, and we reported these, of course, to Google and Samsung, and the Google ones were assigned high severity.
So with this in mind, you may now say, okay, there are CVEs, there's high severity, but is this really an important or realistic attack surface, right? Like, when do I enter a malicious SIM in my phone? It does not really happen every day. We believe that this attack surface consideration really depends on your threat model. Think about for eSIMs, right? Like you download eSIM, or like I, as traveling person, download eSIMs all the time from somewhere, and I not necessarily trust all the operators or really investigated whether they are trustworthy or not. And they could embed such functionality. Similar, physical attackers, right? If you give your phone out of the hand, it may be that a physical attacker just inserts a SIM. Then Tomasz told us about remote SIM update functionality. So over-the-air updates could compromise your phone if you have a malicious or hostile operator which you're not trusting. Or there could be vulnerabilities in the SIM stack themselves, right? We saw it in the past that there were vulnerabilities in the SIM implementation themselves which were abused by attackers to then provide updates, to then abuse proactive features to attack victims. But besides all of this, we also want to provide you an additional line of thought. What if you would not need a custom or an attacker-controlled SIM card at all? What if you can somehow differently trigger the very same vulnerabilities? And that brings us to the last part of our talk, the interposers.
Yeah, so the interposer is this thin device that goes in between your SIM and the phone. It essentially just sticks on the phone, on the SIM, and just slides right into the SIM tray. And what this has historically had been used for is, for example, in Kenya, they try to do banking, so they would give this out to customers. They would put it on their SIM, unknowing maybe to the potential dangers of that. And it would extend the SIM capabilities to also do banking, however they implemented that. But in the modern era, we actually, you tend to find these as carrier lock bypasses, so especially for iPhones. So they're advertised as being able to bypass your carrier-locked iPhone to essentially use any SIM that you'd like from any carrier. And this is a very cheap solution. It only costs around $3 at most.
Yep. So we bought a couple of those, and we had a starting point why we started looking at it. There was one provider which allowed one to create custom firmware for their SIM cards or for their interposers. To create the custom firmware, they offer a web interface where you can basically change the ECC ID and some strings shown in the menus. You can change it around and then download a firmware file. The firmware file turns out to be just a text file, which then goes into a custom software the provider offers and flashes it to a card or to the interposer when it's inserted into a reader together with a card. So looking at one of these firmware update files as downloaded looks something like this, like lots of lines of hex. So we stared at it and stared at it and stared at it, and eventually it started to make sense. These are APDUs. And the repeated patterns really guided us towards the meaning of the different APDUs. Especially we could find one which we believed this one is a flash firmware chunk, which would flash a certain amount of bytes to the next location in memory. So after we found this, we wrote a small parser to turn this text file into a binary file with the firmware. Now, as we had a binary file, we could go again wild and start our standard reverse engineering tools, strings. And also strings here, again, showed us some very interesting insights over the firmware. We saw, for instance, strings indicating what kind of chip was used and what kind of code. In this example, the CCM3310ST smart card demo. So we're definitely right? Like SIMs are smart cards, so there's the functionality we're looking for. We saw some indication of API or hardware abstraction layer calls. In this example, for instance, the acknowledge to reset callback or something to send the ATR. And we also saw the different menu strings which we put into the customization. Following the strings, we found a data sheet, right? We saw CCM3310ST, Googling lead to a data sheet, which is also really interesting because it includes this block diagram, and on there it shows 3 ISO 7816 peripherals. So it's definitely something which has multiple peripherals to interact with smart cards, which seems to be like the perfect basis to implement an interposer. We also got some information about the used instruction set architecture, which was RISC-V, which I at the time find very exciting because it was 2023 when we started this, and having RISC-V in the wild was the first time I at least saw it. So we happily started reverse engineering the firmware, and luckily it mapped directly to address 0x00, so no guessing of the base address, really nice and convenient. It also looked directly like an entry point, like how firmware entry points look like, copying over some data from ROM to RAM and similar, and then going to a never-ending main loop. This main loop is handling incoming APDUs and stores the different parameters like the instruction class, the status words, and similar, all in global variables. Lastly, there is also the peripheral interaction, which we could not find the actual code for in the firmware. We saw, part of it we saw, but most of the interesting ones, like sending data out, is not directly included in the firmware, but part of the hardware abstraction layer. So the chip or the firmware on the chip likely has some sort of ROM memory where the missing functions are there, or the firmware update, as we get it from the vendor, is only partial. Nevertheless, this is already enough to start modifying the RISC-V firmware and seeing where we can get. Right? To recap, our goal is here as a proof of concept to send our malicious payload, which we found, to really demonstrate the dangers of interposers. We used a minimal example proof of concept payload, which triggers the heap corruption we just saw, and only considers of 9 bytes, or consists of 9 bytes. Idea using the low amount of data for the proof of concept is that it's easier to probably bring this over and easier to patch. So we started binary patching the firmware, and we started patching around the fetch or the handle fetch command. Remember, if a SIM notifies the UE that there are proactive data, the UE or the CP, the baseband, will then go and uses the fetch command to get or to fetch the proactive data from the SIM. So we thought we just override this functionality. This is what the handle fetch in the firmware looked like after reverse engineering. So it starts checking the TPDU length and if a proactive command is currently needed to be dispatched. And if everything looks right, it sends out the APDU instruction and the APDU itself. So we modified it. We don't care about this if check. We really just set the APDU length to 9 and mem copy over the malicious payload into the out buffer and send over the APDU out to see whether it crashes. So these are our firmware modifications. Now we had a new binary, but we also need to somehow get it on the card. And it turned out that using the vendor tooling, like it's a proprietary Windows tool, and card readers was for developing this really cumbersome because cards would usually, or like interposers would break very easily when inserted from card readers. So we kind of built our own little flashing and debugging infrastructure, again, based on the SIMtrace 2. And we see here that we have a phone attached right now, but we also have the card reader hanging on the laptop up in the image. And this allows us to quickly change the Flatflix cable from phone to card reader and card writer so that we can easily change the interposer firmware and debug what's going on. It's especially great because it gives us the capability to trace the APDUs, as this is kind of the purpose of the SIMtrace, so we can really see what's going on while testing. And after, I think it took 5, 6, 7 attempts, we got the next demo working. So another phone is coming up.
So here we have the interposer on the SIM tray. I'm not going to pull it out because it's going to fall out, but it's there.
Yeah, and so,
Okay, so
we are ready. So we're inserting it, and now it takes a little while. First, the baseband thinks that the SIM card is removed or disabled. And now we hope that the demo gods are with us. If not, we gotta turn to the backup phone.
should I just replug it?
Yeah, we can. Oh no, here we go. Hey, they're with us. Took a little while, but again, we see we crashed the modem based on the payload being injected from our interposer.
Okay.
All right, thank you. So that brings us to the final remarks of our talk.
So in the future, we kind of also want to work on defenses. With eSIMs, you have a different problem, right? Because with eSIMs, it's embedded, these days it's embedded on MFF2 package IC, and that's soldered directly onto the main board. So to be able to do this attack with the interposer, you would, for example, have to desolder, put it in there, and solder back on, which is probably quite difficult, but we want to try that out. There's also another thing you can do, which is use the interposer instead of to attack, but you can maybe also defend, right? So if you can drop these proactive commands from the SIM to the, like coming in from the SIM to the phone, then you can totally prevent this attack surface from ever being a problem. And then there's also the secure channel protocol, which is standardized for decades already, and but it is just not used by commercial SIMs. So they could probably prevent the entire problem of interposers altogether if they just use this secure channel protocol.
And that brings us to the very end of our talks, a small summary, like what can you take away? First of all, we want you to, and I think we successfully showed that, SIMs are way more than a key value store, but tiny computers with a lot of operations on their own.
Yeah, and as we showed with the proactive commands, as a pretty substantial attack surface, there are lots of different proactive commands, and there's also other things that the SIM can do, other than proactive.
And due to this, we think there's really the need for more research SIM tooling. When we started, the SIMtrace was already around and research SIM cards, and we added to this landscape with SIMurai, but it's really just a start. In our opinion, there's really the need to have more to explore also the other parts of this arcane stack, as it's really at the bottom of computation today, right?
And with interposers being so extremely cheap and easy to modify the firmware of, you can really also have a much easier time developing than using Java cards. And you can probably get a lot of different interesting proof of concepts working with that.
All right, and that's our talks. Here are a couple of links, how to contact us via email, how to get the SIMurai paper or GitHub, or the slides to this talk. Thank you for listening to us.
Thanks.
And we do have some time for questions. So anybody in the audience have some questions? We'll run around and... Yes, come in.
I may have just missed that, but how did you got that baseband firmware out of the Pixel?
Oh, firmware update files. You can download the firmware update files and find it in there.
Okay, so it flashes over some SPI or to it? Or?
No, it's a binary file being part of the general Android firmware update file. So if you download for instance, the factory images or downloads for specific Android versions or similar, you have a radio.img file which includes the firmware.
Thank you.
Anybody else? All right, let's thank Marius and Tomasz again.
Thanks.
Thank you.